What's your minimum specification? In terms of that constant idea, you've spoken about CPU instruction sets in the past, and one of the biggest requests for this interview I got was around your opinion about CPU instruction sets. Specifically how we deal with fundamental limits on them, how we pivot to better ones, and what's your skin in the game in terms of ARM versus x86 versus RISC-V. I think at one point you said most compute happens on a couple of dozen opcodes, so ISA doesn't matter.
Yeah,
Am I
yeah, yeah.
remembering that correctly?
It's a very sad story. Yeah, 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 yeah. No, it's not even a couple of dozen. 80% of the execution is like 6 instructions. Load, store, add, subtract, compare, and branch. And you pretty much covered it. If you're writing in, Perl or something, maybe call and return are more important than compare and branch. But you know, instruction sets only matter a little bit, right? You can lose 10 or 20% because you're missing instructions, or for a while we thought variable length instructions were really hard to decode, but we keep figuring out how to do that. You basically predict where all the instructions are in tables, and once you have good predictors, you can predict that stuff well enough. So fixed length instructions seem really nice when you're building little baby computers, but if you're building like a really big computer, the predictor to figure out where all the instructions are isn't dominating the die. So it doesn't matter that much. And when RISC first came out, an x86 was half microcode. So if you look at the die, half the chip was a ROM, maybe a third or something. And the RISC guys could say there's no ROM in a RISC chip, so we get more performance. But now the ROM is so small you can't find it. Actually, the adder is so small you can hardly find it. Right? So what limits computer performance is predictability. And the two big ones are, instruction predictability and branch predictability and data locality. And now the new predictors are really good at that. They're big. Like the predictors are way bigger than the adder. Right. And that's where you get into the CPU versus like GPU or AI engine debate.
Yeah.
Like the GPU guys will say, look, there's no branch predictor because we do everything in parallel. So the chip is way more adders and subtractors. And that's true if that's the problem you have, but they're crap at running C programs.
Yeah,
And
it's all about crafting the software at the compile time, right?
yeah,
If you can
and
do that
then
well, then
GPUs were built to run shader programs on pixels. So you're given like 8 million pixels, and so the big GPUs now have 6,000 threads. So you can cover all the pixels with each one of them running 1,000 programs per frame. But it's sort of like an army of ants carrying around grains of sand. Whereas big AI computers, they have really big matrix multipliers and like a much smaller number of threads, essentially, that do a lot more math because the problem is inherently big. Whereas the shader problem was the problems were inherently small because there were so many pixels. So there's genuinely three different kinds of computers: CPUs, GPUs, and AI. And then NVIDIA is kind of doing the tweener thing where they're using a GPU to run AI and they're trying to enhance it. And some of that's obviously working pretty well, and some of it's obviously fairly complicated. And so it's an interesting, and this happens a lot. Like general purpose CPUs, when they saw the vector performance of GPUs, added vector units, and sometimes that was great because you only had a little bit of vector computing to do. But if you had a lot, GPU might be a better solution.
So many people are asking, what do you think about ARM versus x86? Which one has the legs? Which one, has the performance? Do you care much? Or
Um, I care a little. Like, here's what happened. So when x86 first came out, it was super simple and clean, right? And then at the time, there was multiple 8-bit architectures: x86, the 6800, 6502. I programmed probably all of them way back in the day. And then x86, oddly enough, was the open version, right? They licensed that to 7 different companies. And then that gave people opportunity to put in tape. But Intel, surprisingly, was both licensed it in one long run. But then they went to 16 bits and 32 bits, and then they added virtual memory, virtualization, security, 64 bits, and then more features. So what happens to an architecture is as you add stuff, you keep the old stuff so it's compatible. So when ARM first came out, it was a clean 32-bit computer. And compared to x86, it just looked like, way simpler and easier to build. But then they added a 16-bit mode and the IT instruction, which is awful, and a kind of a weird floating point vector extension set with overlays in a register file, and then 64 bits, which partly cleaned it up. And they added, there was some special stuff for security and booting, and so it slowly got more complicated. Now RISC-V shows up, and it's the shiny new cousin, right? Because there's no legacy, and it's actually an open instruction set architecture, and people build it in universities where they didn't have time or interest to add too much junk, like some architectures have. So, relatively speaking, just because of its pedigree and age, it's early in the life cycle of complexity, and it's a pretty good instruction set. They did a fine job. So if I was just going to say, I want to build a computer really fast today, and I want it to go fast, RISC-V is the easiest one. It's the simplest one. It's got all the right features. It's got the right top 8 instructions, that you actually need to optimize. It doesn't have too much junk. So, yeah.
So modern instruction sets have too much bloat, especially the old ones, because they've
Well,
got too much
no.
legacy baggage.
Instruction sets that have been iterated and added to will have too much bloat.
Yeah.
That's what always happens, right? So as you keep adding things, like, the engineers have this struggle, right? You have this really good design, and there's 10 features, so you add some features to it. The features all make it better, but they make it more complicated. And as you go along, every new feature you add gets harder to do because the interactions with that feature and everything else gets terrible. And the marketing guys and the old customers will say, don't delete anything. But meanwhile, they're all playing with the new fresh thing that's only does 70% of what the old one does, but it does it way better because it doesn't have all these problems, right? So this is, I've talked about diminishing return curves. There's a bunch of reasons for diminishing returns, but one of them is the complexity of the interactions of things slow you down to the point where something simpler that did less would actually be faster. And that's happened many times. It's some result of complexity theory and human nefariousness, I think.
So do you ever see a situation where x86 gets broken down and something just gets reinvented, or will it just remain sort of legacy and then just new things will pop up like RISC-V too?
Well, Zen was a fairly clean slate. It obviously had to carry along baggage for this and that, but they deprecated a lot of the old 16-bit modes and bats, and there's a whole bunch of junk that disappeared. And sometimes if you're careful, you can say, all right, I need to support this legacy, but it doesn't have to be performant, and I can isolate it from the rest of the design.
Emulate it and stuff.
So, yeah, emulate it or support it. And we used to build computers such, that you had a front end, fetch, dispatch, execute, load, store, L2 cache. And if you looked at the boundaries between them, you'd see like 100 wires doing random things that were dependent on exactly what cycle of or what phase of the clock it was. Now the interfaces tend to look just like instruction boundaries. I send an instruction from here to there, and then I have a protocol that says act. So the computer inside doesn't look like a big mess of stuff connected together. It looks like 8 computers hooked together that do different things. There's the fetch computer and the dispatch computer and the integer execution computer and the floating point computer. And if you do that properly, you can change the floating point without touching anybody else. And again, that's less of an instruction set thing than what was your design principle when you built it, and then how did you do it, and were you faithful to that? Because the thing is, you get to a problem, you say, boy, if I could just add these 5 wires between these 2 boxes, I could get rid of this problem. But every time you do that, every time you violate the abstraction layer, you've created a problem for future Jim. Right.
Future Jim.
like
It's
like I've done that so many times. It's like if you'd solved it properly, it would still be clean. But at some point you always have to hack a little bit, and then that over time that kills you. So